Okay, this is lecture 21. So we will finish our discussion on the Schappeter-Gummel scheme today, and that will be the last lecture for our conventional steady-state DD simulation. So today's lecture will be quite short because I wanted to give you some chances to catch up our lecture progress. So let's just finish the Schappeter-Gummel scheme. Yes, this slide was taken from our previous one, Bernoulli function. So we have already covered all important properties of this Bernoulli function. So its definition is shown here, and it looks quite easy to understand. But in actual implementation, please be careful when we have x quite close to 0. In this case, this upper part and lower part, both of them approach it to 0. So we have some numerical difficulties. So what we do in usual is just to split this function into various cases depending on the absolute value of x value. So if x value is lower than certain value, then we can use certain Taylor expanded form. And if it is beyond that value, then actually we can use the conventional form. And another rare case is if we have too large x value, then sometimes this exponential function can give us too large numbers. So this exponential itself gives us infinity number. Once we have this infinity number, then minus 1 will give us once again just infinity number. So division by this infinity number can happen. So please be careful about this one. So I think that's it for implementation of our Bernoulli function. Okay, so and please remember that we have already covered the extreme forms of our Schappeter-Gummel scheme. If we have x equal to 0 or quite close to 0, then you know that here we have this condition. Bernoulli function does not contribute any special number. Then here we have certain things like this: 1 minus certain Bernoulli function minus an I Bernoulli function, also certain input argument. Of course, this and that are in opposite in their sign. However, anyway, if we have very close to 0 and very close to 0 values as input parameters, then actually this Bernoulli function does not contribute any special role. So we will have just a simple form like this. So what is this? This is corresponding to diffusion. So simply speaking, when we have small potential difference between two nodes, then it is cascaded into the diffusion form. On the other hand, if our, for example, phi plus 1 minus phi I divided by sum over J, that is one coefficient, and that is another coefficient, the same one with a different sign. And if we have, for example, let's say this first input argument is quite large, so much larger than 1, then it means that it is much smaller than minus 1. Then what will happen? In this case, this first one actually goes away, and this one just becomes minus phi I v over t, because the asymptotic behavior of our Bernoulli function when it is approaching to the negative infinity is just to follow Bernoulli function follows minus x for this limiting case. So isn't that you can easily understand once again this is corresponding to the diffusion dominant drift dominant behavior of our current density expression. So that was already covered in our previous lecture. So today we will discuss a little bit more about the real implementation. So of course in the next slide I will explicitly show what will happen we just make correct discretization or Jacobian matrix. However, in order to implement that one, so we need something like this, the derivative of Bernoulli function. So here we have Bernoulli function which is given by once again x exponential x minus 1, and please note that this is like a function of phi I plus 1 and phi I. If we have to certain partial derivative of, for example, let's say that Vt phi I plus 1 minus phi I. This is a typical case we have, and let's say that we have to make this partial derivative. Then what we can do is just round b this function, this input argument with respect to also this input argument. Okay, also here we have Vt and multiplied by just 1 over Vt, because you know this is once again partially derived with respect to phi sub I plus 1, so it will give us 1 over Vt. So we need this quantity round b over round x. So this quantity is needed, and how can we do that? So please have a look at the original form of Bernoulli function. Then what we can do is, okay, if we take the derived form, then first this x is derived, then here we have 1 over exponential x minus 1. This is corresponding to the first one. And the second one will be, obviously, we keep the x and calculate d over dx of exponential x minus 1's minus 1's power. Okay, so that is not that difficult to actually evaluate. So let me just follow, just to keep the first term, it is already done, and x, and we will have now minus sign due to this minus x times exponential x minus 1's minus square. So once we have this form, we can easily understand x times exponential x minus 1's inverse is corresponding to our original Bernoulli function. So this function can be once again written as Bernoulli function itself times exponential x minus 1's inverse. So that is also okay. Oh, sorry about that. Once we take this one, after that we have to also, sorry about that, I made mistakes here. We must evaluate derivative of this one. However, this minus 1 is gone, but this derivative of exponential x will give us once again exponential x. So sorry about that. Then here we have exponential x. So that will give us exponential x. So now we understand. Here we have a b over x and minus sign comes from this one, and exponential x divided by exponential x minus 1. Of course, we can make different expressions for this derivative, but it is better to have it because we have already implemented the Bernoulli function. So maybe reuse it is quite a good approach. Anyway, even in this case, if we have quite a small x value, then that will give us some problems. So care should be paid even for this derivative of Bernoulli function. Okay, so now you can understand this is. So although it looks like just ever increasing function, but please note that here we have 0. So dv over dx is always negative, as explained in our previous slide as a monotonically decreasing function. So that is not that difficult. So now let's go to the Jacobian. So of course we must consider not only the electron continuity equation but also whole continuity equation. But in this slide I just show you only electron current density as a representative example. So for whole one, so please do your exercise. This is nothing but just a restatement of our electron current density. So Q dN over delta X times something originated from Shapiro-Bellman scheme. So how can you memorize it? Actually, please note that this is corresponding to just a diffusion term when we have B equal to 1. What is B equal to 1 case? This is corresponding to zero potential difference between two node points. So please always consider diffusion term as a reference form. After that, just add this and that Bernoulli function correction. Then you will have the relation. Then now let's say that since we have this form, actually what we can do is, first of all, take the partial derivative of this current density with respect to the electron density, and later with respect to electrostatic potential. Of course, all of these four components should be considered exactly in order to get good convergence behavior. So of course you will implement it by yourself, and you will find that any mistakes in this implementation will give you the degraded convergence behavior, or sometimes even diverging behavior. So please be careful not make any mistakes in its implementation. Well, let's do it together with me. So how about this one? We wanted to make the partial derivative with respect to the electron density at x sub I plus 1. Well, this is just a constant, then we can just keep it here. Then the remaining task is quite simple. Here we have a certain complicated term. However, in terms of n sub I plus 1, we have just a linear function. So if we take a partial derivative, then we will get this Bernoulli function only. This one comes here. And how about this second term? Although it has also complicated form, but since it is just dependent on n sub I, not n sub I plus 1, entirely it vanishes. So we will have this form. Okay, so are you with me? And another one with respect to n sub I, then the case is the opposite. The first term goes away and second term gives us just a minus Bernoulli function. So what does it mean? What it means is, okay, please have a look at this part. Here we have certain inequality. Here we have q times dn over delta x. Let's assume that this is a constant. Then here we have only positive constant. Then here we have only one Bernoulli function. And what was the property of Bernoulli function? It is ever monotonically decreasing function. However, at the same time, it is always a positive function everywhere. So now we can say that, okay, although we don't have the exact value of a Bernoulli function, it depends on the potential difference, but we can certainly say that this component is always positive. On the other hand, the partial derivative with respect to this electron density at a central node or ith node can be always negative. Okay, so let me just emphasize this one later. So in the previous slide, I just considered the partial derivative with respect to n something, n sub I plus 1 or n sub I. Also, we can ask this question. Okay, if we have this one, Jn defined at I plus a half position, then how about Ni minus 1? So we are now talking about the flux between xi and xi plus 1. Then how about its dependence on the electron density at here? Or how about the dependence on Ni plus 2, the electron density defined on x sub I plus 2. Obviously, that will be just 0. Otherwise, this subscript is equal to I or I plus 1. Then we have non-zero values. For all other cases, they are vanishing. Okay. Then how about the potential difference? Following the similar law, then we can say that it will only depend on phi sub I plus 1 and phi sub I minus 1. If we wanted to calculate the partial derivative with respect to I plus 2, then that does not contribute at all, because this is just a potential not related with this edge. So everything is just localized between x sub I and x sub I plus 1. So then it is just restated once again here for your reference, and I want to take the partial derivative with respect to phi I plus 1. Then what will happen? Obviously, this n does not depend on electrostatic potential. It is another independent variable. We just keep it and we must take a partial derivative. Its partial derivative can be obtained by not only this one, no, here we have 1 over Bt. So are you with me? It is because this B prime is not derivative with respect to this quantity, but it is the derivative with respect to this entire quantity, and we must consider once again the d over d phi I plus 1 of Vt phi I plus 1 minus phi I. So that will give us this additional factor 1 over Vt. So anyway, once we adopt this notation b prime, then life becomes quite easier. So please try to implement both of the Bernoulli function and its derivative, so you can easily understand. Here we have certain numbers. So now previously we had, here we have something, previously we had this negative sign, but here we have positive sign. What happens? Because here we have a negative sign. This negative sign gives us actually 1 over minus 1 over Vt, so that is combined here, they are combined here, and gives you just a positive number. Okay, so now you can understand the partial derivative with respect to certain potential can be also done without much difficulty, as much as you just mechanically, routinely apply the chain rule into your current density expression. Once you apply this kind of mechanical operation, then you will get the, although looks a little bit complicated, but you can get it. Okay. Okay, so this is the last slide that I have prepared for this line, but I wanted to tell you one important thing. So, not prepared in my slide, but let me just come back to here. This is related with j sub n. However, what is actual value you must implement in your calculation? For example, so for your electron continuity, your electron continuity equation is not like this: Jn xi plus something equal to 0. This is not your electron continuity. What is your electron continuity? Actually, when you consider your electron continuity equation, for example, let's say that instead of this one, let me just write down, for example, f for y, so defined on xi. This is given by Jn minus Jn equal, sorry about that, minus 0.5 equal to 0. This is the form of your electron continuity equation. So if you wanted to calculate a certain component of your Jacobian matrix, for example, let me just give you a certain number, 3 times, to be quite concrete, I wanted to try this example. So please try to read the physical meaning of this component. This is your Jacobian matrix, and what is this? This is corresponding to the row index, and position is x sub I, and this is corresponding to your electron continuity, so nothing but this one. And what is this? This 3i plus 1 is corresponding to, once again, your x sub i's position and electron density. For example, if we take this kind of arrangement, so then we will have this one. Of course, if we swap hole and electron, then that will be 2 and 2, but I just did 2, phi and p order to arrange them. So then what will happen? In order to evaluate this one, then we must consider this one. Round Jn x sub I plus half with respect to n sub I. But it's not all for this flux term. Of course, we have made something for this j sub n. However, we have another one. So how can you implement it? Then in this case, we must minus jn x I minus half and partially derivative with respect to n sub I. So are you with me? The point is, I wanted to ask you the sign of each term. So please try to estimate the sign of each term. What is the sign of this term? So as I told you, here this is always negative. So are you with me? And please have a look at this one. What is the sign of this term? The sign of this term is always positive because this is corresponding to the, in some sense, right node, not the left node. So for right node, we have a positive number. However, here we have once again minus sign. So overall, I wanted to say that the Jacobian matrix, the diagonal component originated from your electron continuity is always has a negative sign. So are you with me? So, but what is the meaning of this one? Let me just do a similar thing. Really. For example, I want to ask you another similar problem. A sub 3i plus 1, comma, however, column index is 3 times I plus not 1 but 4. What is physical meaning of this quantity? This is corresponding to our flux. Flux is the same because the row index is the same. However, we must calculate the partial derivative with respect to now n sub I plus 1. Then what happened? This one will contribute and this one will not contribute because this is the flux between x sub I minus 1 and x sub I. So we will have just round jn xi plus half partially derivative with respect to n sub I plus 1, and that is always, as shown here, always has positive sign. So following the same argument, we can say that a sub the same row, however, minus 2, that will have also positive sign. Okay, so right now you cannot understand what I'm talking about, but let me just go to here. Here we have a Jacobian matrix written as A matrix. And where can we find our continuity equation for x sub I node? Let's say that here we have a certain row corresponding to our x sub I point. That will be 3i plus 1. This is a part of our Jacobian matrix. And let's assume that this is the diagonal component. So diagonal component, this one is corresponding to 3i plus 1, comma 3i plus 1. And now, I just told you that this is corresponding to always a negative number. And here we have another neighboring numbers and another neighboring numbers. Its column value is 3i plus 4, or its column value is, column index is 3i minus 2, and we can say that this is positive and this is positive. So I'm just repeating my previous argument once again with this drawing sketch for our Jacobian matrix. Point is, they have distinct signs. Diagonal component has a certain sign, but this non-diagonal, off-diagonal component has exactly the opposite signs. Okay, so that is the important one. For example, it's like this. If you have a certain matrix, let's say that you have something like minus 2, 1, 1, minus 2, 1, 1, minus 2, 1, 1. You have seen it quite many times, and you can easily understand. Here you have a certain diagonal component which has certain distinct sign, and when you have a look at this part, what happens? Then you can find that they have all the opposite sign against this diagonal component. So of course, this is not a general matrix. For example, let's say that we have 1, 2, 3, 4. Is it has such kind of a property? Actually not. It has positive sign and positive sign. They do not have distinct signs. However, if we have minus and minus, then we can say that diagonal component has, all diagonal component has a distinct sign, and all other off-diagonal component has the opposite sign. That is quite impressive, and that is quite important. So I wanted to say that when you make this Jacobian matrix, especially for your electron density, then you can have very important property, like all of your off-diagonal components and diagonal components do not share the sign. Why that is so important? So please think about this one. What is the physical meaning of these three components? Here, here, here. The physical meaning of our electron continuity equation is just counting number of electrons inside this area. Let's say that this is x sub I and xi plus 1 and x sub I. Let's say that we have a certain electron density. Okay, this is the electron density, the solution. The point is, Jacobian matrix just describe what happens if we slightly change this equation, then what will happen to the residue value. For example, if we slightly increase the electron density at a center point, or if we slightly increase the electron density for neighboring points, what will happen? That is the situation. For example, let's say that this is the correct value. We are happy with it. But intentionally, we just increase the electron density into a long value. Then what will happen? So then everything is just a solution. Then the error is highly localized on this node. Then what we can expect is, okay, this one will eventually go to this way or that way. So when we measure the flow of our electron movement, then okay, we will say that there will be a net loss of electrons. That will be the expected behavior of our electron density. But let's say that now we have an error intentionally occurred not in this central node but intentionally introduced in this neighboring node. Then what will happen? Obviously, this error will introduce additional flux, and that additional flux will be just this way or that way. But this one is not of our interest because we are interested the increase or decrease of electron density here. So what we can expect is once we have a certain increased electron density in this x sub I minus 1, then it will make net gain of electrons from the viewpoint of this central node. Same happens for this right side node. If we have additional electrons, then that will eventually contribute to the net increase of electron numbers inside this central node x sub I. So what we can expect is this distinctively different signs of our Jacobian component is corresponding to the correct behavior of our electron movement. However, let's assume that one long case, for example, minus sign. What does it mean? It means that even though we introduce an increased electron density here, but the electron density in this position is actually decreasing. How can that happen? It's not possible in our physical world because in the worst case, let's say that all of our injected electrons just flow away into the left side, but that does not change anything in this central node. However, if you make a long discretization, then you will have eventually this long sign for your Jacobian matrix. So what I wanted to ask you, not an official homework, but just checking for your understanding, please visit your previous naive discretization. Not this one, not this Chapeau-Gomez scheme. So why don't you just come to our previous one? So we have some time. Yes, so here, can you see it? Here, instead of this Chapeau-Gomez scheme, now we have our previous naive implementation. Then what I wanted to ask you is please try to evaluate the diagonal component and off-diagonal component of your Jacobian matrix, and please try to figure out whether you have well-defined sign relation or not. My answer is when you examine this naive discretization, you will find that when you have strong enough potential difference, then your discretization does not support such kind of a sign relation. It means that your discretization fails to describe the correct physical behavior. Okay, so the drastic failure of our discretization shown in, not in this one, but in lecture 18, I have shown that the failure of naive implementation, and you have seen those kind of negative densities, so it was quite awful, and it was all related with this kind of failure in predicting correct physical behavior. So Jacobian takes over. So that is quite important. So please, although it is not my official homework, but please check your naive implementation. Okay, then now let's go to the improved result. I assume that now all of you successfully implement the Shapeter-Gomez scheme. Then what will happen to your result? For example, this is equilibrium electron density for a p-n junction, and we just keep the same number of mesh points. So this old and new means that this old is our naive implementation, and this new is corresponding to Shapeter-Gomez scheme. And what happens? Here previously for this coarse mesh, so we had really awful result because here and here and here and here, all these points we have negative electron densities, so that is not acceptable to us. So that was a drastic failure of our discretization. However, Shapeter-Gomez scheme just predict the same solution that is corresponding to the solution of a non-linear Poisson equation. Good, but this is just for equilibrium case. And another one, if we're talking about non-equilibrium case, let's check about the doping dependence. So previously we had, this is a more dense point. So previously in the previous slide, this one shows intentionally use quite a coarse grid, but now we have quite fine grid, more than 100 points are used, so nothing related with this coarse grid. But when we introduce certain doping density, so then when we have this doping density, we can find some negative electron densities in those points, but that is also gone in Shapeter-Gomez discretization. So simply speaking, Shapeter-Gomez scheme at equilibrium shows an excellent agreement with the solution of the nonlinear Poisson equation. So it is quite good behavior, but this is not that all, because we must consider non-equilibrium cases. So now let's have a look at this one. Previously I showed you that when we use quite a coarse grid system, then our naive implementation just to lose the current. For example, if we use almost 800 node points, then our current is quite accurate. But if you use lesser number of points, then it drastically decrease, and with just 100 points your current density is almost diminishing. So now let's say that if you don't have this kind of a new technique, then if you just generate a certain numerical result for your Ford IV, then can you believe your result? Actually not. You don't know whether your grid point is located here or there or somewhere here. So what you can do is always increase the number of mesh points and check whether, although I have spent certain, for example, 400 mesh points, but my current seems to be just 3.0. Without this test, I cannot assure that my current value is correct. So unfortunately, we have to increase the value, or number of points to get the convergence in its anode current. However, when you have a look at this Schapter-Gummel scheme implementation, what happens? Even though it shows a little variation here, but you can see that more or less its current level is stable. It means that even when you just use 100 relatively small number of points, but it is guaranteed that your current is reasonably well matched to the solution of a fine grid. So that's the reason why you can use this small number of points for your real implementation. So without this scheme, Schapter-Gummel scheme, we cannot nowadays perform this three-dimensional device simulation, because if we say that if we have to spend at least 1000 points along one direction, then what will happen to our three-dimensional simulation? 1000 its cube give us 10 to the 9, and 1 billion node points are required for three-dimensional case. If we can reduce it to 100, then what happens? Then its cube gives us just 1 million. Nowadays, in our computing power, the difference between million and billion node points is huge. Actually, million mesh points can be handled. Billion mesh points, it is still beyond, sometimes too many of us, beyond the capability. So, this is the situation of 2023. And what was the situation in its invention? In the 70s? And what was computing power? At that time, even this one-dimensional simulation was quite heavy to our pioneers. So to them, the number of grid points was much more critical than to us. So they eagerly needed stabilized scheme to solve this continuity equation, and they succeeded to get the Schapter-Gummel scheme. So I can certainly say that without Schapter-Gummel scheme, we cannot simulate this electron continuity equation and hole continuity equation in a stable manner. It means that there is no field like device simulation. Okay, that is really important. Okay, so okay.
그 샤페트 구매 스킨 썼을 때
Mhm.
메쉬에 따라서 이 값이 올라가기도 하고 내려가기도 하는데
So there is a little fluctuation here. Yeah.
그럼 메쉬에 따라서 메쉬가 잘게 될수록 좀 더 정확한 시뮬레이션이 가능할
Sure, sure.
텐데 이런 부분에서 보면 어떤 게 좀 더 정확하다라고 이 뒤에서도 그 플럭쉐이션이 계속 흔들리면서 뭔가 진행이 되나요?
If you go beyond a certain position, so I'm not saying that this 800 is perfectly matched, but you can say that if we go to beyond certain criterion, then we will have almostly indistinguishable values for different mesh points. And here you can see that there is a little differences. But this is not related with actually the not only the failure of Shaped-Goumel scheme, but we are considering really abrupt p-n junction in this case. So depending on the number of points, so maybe the treatment of this metallurgical junction can differ. So if we have 100 points, then there will be certain this is the end point of your n-type region, and this will be the end of your p-type region. So for 100 points, and if you spend more points, then what will happen? Then eventually you will have more abrupt transition here. Although even in this case you have assumed the abrupt transition, but there was certain space between 2 points, and now this space is reduced, so we cannot say that with different number of mesh points our tested systems are perfectly matched, and so it is difficult to say. So therefore such kind of fluctuation, small fluctuation here observed here is quite much acceptable. So of course it is always recommended to sufficiently high number of points, but who knows, in practice we are enforced in many cases to stop some reasonable value of number of points. Okay, thank you for your question. And do you have any question? So that that's the reason why still we are celebrating this Shaped-Goumel scheme. Without this Shaped-Goumel scheme, our entire field does not exist. Okay. So now let's go to your homework. So now you have 1 week to prepare your homework report. So the problem 1 for equilibrium, and problem 2 is for non-equilibrium cases. So in your previous homework number 13 and 14, you have studied 3 p-n junctions at equilibrium with nonlinear Poisson equation and drift diffusion simulator with naive discretization. But now you have the Shaped-Goumel discretization. So please implement your Shaped-Goumel discretization. Then please simulate this equilibrium electron density and hole density. You can find the drastic improvement over your homework number 14. And now with this well-developed Shaped-Goumel scheme, then you can try to calculate fold and reverse ivory characteristics of those p-n junctions. So simply speaking, you can regenerate or reproduce such kind of behavior, so well matched IV characteristics. So that's it. So the purpose of this homework number 15 is quite simple. So just implement Shaped-Goodman scheme into your code. If you have already done your naive implementation, naive discretization, then the only thing you have to do is just to introduce better implementation into your Jacobian matrix and residue. Then in order to get those goals, you have to implement the Bernoulli function and first derivative of your Bernoulli function. So please implement those two functions and test it. If your Bernoulli function implementation or its derivative contains certain bugs, then actually you will fail. So please first test your Bernoulli function and its derivative, and once you believe that, oh, I have done it sufficiently well, then please use your implementation into it, and please explicitly show how did you implement your b function and db over dx function. Okay, that is important. Okay, do you have any question? If you don't have a question, then I will just show you my last slide in today's lecture. And due is 1 week, so please understand, I don't expect your failure. I mean that the reason is, since this is the most important part of our entire semester, I hope that all of you successfully follow the lecture progress. So please, I give you 1 week long term, and also you have already sufficient time from our previous homework number 14. So please catch up our lecture progress and successfully implement the Shaped-Goodman scheme. So sometimes you will have some convergence failure, then don't be too much frustrated. Please, always when you have such kind of failure, then please come back to the basic. That's the reason why I intentionally introduce problem number 1. Problem number 1 is relatively easier to you because this is equilibrium case, and in equilibrium case you have many other tools for your comparison. For example, your definite reference would be nonlinear Poisson equation that will give you the exact solution. So whenever your implementation shows some deviation from nonlinear Poisson equation solution, then something is wrong for your implementation. And I think that your also naive implementation you have done in the previous lectures will give you certain starting point for your implementation. So please, and what I wanted to say here, please have a look at this one. Please have a look at this number. This is nothing but the very first update I got when I start the Shaped-Goodman simulator. So I got a solution from nonlinear Poisson equation, and when I use this nonlinear Poisson equation solution as an initial solution for our Shaped-Goodman discretization, then the update of potential is corresponding to 10 to the minus 14. It means that it is already in the numerical error range. So once you get the solution for nonlinear Poisson equation, then actually you start from the solution. If everything is correct, then your residue vector itself should be very close to a null vector. If you have certain meaningful number quite much deviate from your zero value, then that component have wrongly calculated. So please understand this situation. So I think that the best way you can do is first try to solve your problem number 1, matched 4 equilibrium case. So I hope that all of you in this classroom successfully perform lecture, non-lecture, homework number 15. And this is my last slide. Okay, so we are now closing to the end of our semester. We have 5 remaining lectures. Today was the last lecture for DC-DD simulation, and my remaining lecture plan is I will spend 3 more lecture hours for transient simulation. So in the transient simulation, starting from very basic, quite a simple system, eventually I wanted to go to the transient simulation of our PM junction, hopefully. So once we achieve this goal, then we will go to the small signal analysis. This is particularly important when we consider certain problems like frequency domain analysis, or sometimes variability, or yeah, sensitivity. Those kind of analysis, for those kind of analysis, this small signal analysis is fundamentally important. So that's the reason why I spent our last 2 lecture hours to this important topic. Of course, depending on the lecture progress, it may change, but I hope that we can consider this important topic in this semester. And my final announcement is term project. Okay, so once again I wanted to stress that term project due date is December 18th, and before 8 o'clock please submit a recorded video via email. So not this LMS system, but please send it to me directly using your email. Okay, so since this is so important, if you fail to submit a recorded video by this due, due deadline, then you will get the immediate failure of your class. Okay, even though you have successfully done many homeworks, but that is directly related with your immediate failure. So please concentrate on term project, and it is important. Okay, so do you have any question? Okay, if you don't have any question, although we have 10 more minutes left, I will wrap up today's lecture, and please concentrate on do your homework number 15 and prepare your term project. Okay, thank you.